Hello and welcome back to the online course on Causal Inference from Observational Studies, NICER 201. We are in the second session of the topic on directed acyclic graphs. And in this session, we'll talk about some of the rules that govern the structure and assumptions made in the directed acyclic graphs. If you think of DAGs as sort of a game, then the goal of that game is twofold. One is to keep all the causal paths open. That is the causal paths between the exposure and the outcome, because that is the path on which the exposure would cause the outcome. The second goal is to keep all the non-causal paths between the exposure and outcome closed. And since these non-causal paths could actually be the source of any unwanted associations between the variables that can actually distort the true causal associations between the exposure and the outcome. So keeping in mind these two goals, we will see how to deal with the various variables in the DAGs. So coming back to our example of the DAG, so here we saw that there were the two of the four paths. There are two causal paths, which is ED and EMD, and there are two non-causal paths, EKD and ECD. Just to remind you once again, causal paths are paths which were starting from exposure up to the outcome, the entire path is in the direction of the arrow, whereas non-causal paths is not so. Now we need to see of these causal and non-causal paths, which ones are open and which ones are closed. And in its natural state, in the way in which we are observing the relationship between these variables without doing any adjustments or selections or any modifications, or what we call as conditioning of the covariates. Before that, what is the state of each of these paths? Remember, the goal is to keep all causal paths open and all non-causal paths closed. So if we look at the two causal paths that we have, ED and EMD, both of these are open. Why are they open? Because there is no collider on that path, which is consistent with the goal of the game. Then we have two non-causal paths, EKD and ECD. The path EKD is closed if we do not condition on the variable k. So there is a collider on the path EKD, k is the collider, and hence it is closed in its unintervened state, which is what we want, right? We want non-causal paths to be closed. However, if we look at the path ECD, since there is no collider on this path, but it is a non-causal path, but it is open. And this kind of path which is what goes against the rule of the game, which says that all non-causal paths should be closed. So this ECD, which is an open non-causal path, could be problematic for us in terms of making the causal inference for the effect of E and D. Now let us see how the state of the paths change if we start conditioning or adjusting for the covariate. Let us start with let's say we adjust for the covariate M, right? So here for that, we designate that by putting a circle around the variable M. And now, so what has this resulted into? We had two open causal paths before we conditioned on M, ED and EMD. After conditioning on M, ED still remains open, which is what we want. However, now because of conditioning on M, we have closed the causal path EMD, which is against the rule of the game, where we say that we need to keep all the causal paths open. However, this does not affect our non-causal paths. So EKD remains closed and ECD remains open. So now we have so earlier when we did not condition on M or any other covariate, we had only one problem at hand in terms of an open non-causal path ECD. Now by conditioning on M, we've created an additional problem for us in terms of making a valid causal inference between E and D, is that we have closed one of the open causal paths, EMD. Now let's see what would happen if we condition on K. Remember that K is our collider. So when we condition on a covariate, which is a collider, the rule of the game says that we have to create an association between its parents, right? So here we have the parents of K are E and D. So we draw a dotted or a dashed line between E and D to represent an association or a relationship that has been induced or created artificially because we have conditioned on the collider. This phenomenon is also known as moralizing the graph. Now, what happens to our paths when we condition on this collider? K, our two causal paths remain open, which is fine, well and good. However, now the earlier path EKD, which was a non-causal path, and it was closed, and which is what was required. Now, because of conditioning on the collider, we have created an association or induced an association between E and D, and hence opened a new path and created a sort of a spurious association between E and D when it may not have existed. So we have opened this non-causal path. And we also had another open non-causal path, which was ECD. So again, now we have created more problems for us in terms of making the causal inference between E and D. Finally, let's see what happens if we condition on our third covariate, which is C. Conditioning on C or adjusting for this particular variable keeps our two causal paths open. ED and EMD remain open. EKD, which was closed in its natural state, remains closed. And ECD, which was a non-causal path and it was open, is now closed. So by doing so, we have now, in fact, ticked all the boxes. Now all the causal paths are open and all the non-causal paths are closed. All of these rules that I've mentioned can be summarized into what is known as the D separation criteria or the directed graph separation rules. What this D separation criteria suggests is that when there is no collider on a path, those paths are unconditionally, which means when we do not adjust for or restrict any variable on that path, those paths remain open. And so with that rule, we can say that every directed path is open. And whenever we have a collider on the path, it unconditionally remains closed. And hence, if there is no open path between two variables, it means that these two variables are D-separated, or in other words, that there is no association, no relationship between these two variables. And hence, also finally, whenever there are open paths, those are the paths which are the only source of the true association between the variables, the exposure and the outcome. And those are what we call as the open causal paths. What happens when we condition on certain covariates? As we saw earlier, conditioning on a non-collider variable will actually block that path. A non-collider variable, for example here, could be an intermediate variable. So here Z is an intermediate between X and Y because the effect of X on Y happens through Z. We have an arrow going from X to Z and Z to Y. Or there could be a condition where Z could be a cause of both of these variables. Right? Z leads to X and Z also leads to Y. So now if we condition on this Z, right, we would be removing any association between X and Y. So conditioning on a non-collider will block that path, which we will be removing the association between X and Y. In the case of when Z is an intermediate, we would not want to do that, right? Because one of the ways in which X causes Y is through Z, and hence conditioning on Z is not appropriate. However, when Z is a cause of both X and Y, XZY is a non-causal path, and we wish to close that non-causal path, and hence it would be appropriate to condition on Z in such a situation. Secondly, conditioning on a collider on a path or any descendant of the collider or any combination of this will open the path, right? Remember here, for example, U is a collider between X and Y, and W is a descendant of the collider U. So if we were to condition or adjust for either U or W or both of them, it would actually induce kind of a spurious association between X and Y, which will again distort the true causal association between X and Y. So in summary, we can say that conditioning on a variable essentially reverses its status on the path. If we condition on a variable which is on a closed path, it will open that path. If we condition a variable which is on an open path, it will close that path. In subsequent topics, we will see how to apply these rules, the D-separation criteria, so that we can identify confounders or sources of selection bias and then do the conditioning or adjustment, as we will see subsequently, so that we can make appropriate causal inferences. And this is how we actually use the D-separation criteria in the directed acyclic graphs to actually help us in designing our studies, which are as free from the biases related to confounding and selection bias as much as possible. Thank you.